I say, is the following frame sufficient? And I show a frame up there. Each one of them happen to be loaded with the same amount, which starts to help things. But then they're not all rotated in the same manner. These are all plan views. If I was looking down from above at these cross sections of these columns, this is what they would look like. And we're going to be talking about failure in the plane and failure out of the plane. This is just something that I use to explain kind of which plane that we're talking about. So this is a portion of a 3D member, or 3D system. And we're talking about just the failure of this frame. And I say, is the frame sufficient? And we're going to actually work this problem coming up. But we're stuck with just talking a little bit theory first. And I say, when checking failure of a sway frame, one must check individual column failure in a no sway mode. That's with pin ends, or a k equal to 1, in plane and out of plane. And also as a group. We've never done this group talk before, at least not in this class. And the reason that we use this k equal to 1, I guess let me slow down here. I basically, all this is really saying is structural resiliency says that the system isn't going to fail until either it fails as a group or if a single member becomes overloaded. So in this case, if one of these singles members become overloaded, then it may fail, or the whole thing would fail and lean over as a group. And if it leans over as a group, if we draw the deflected shape, this would be straight. Where's my straight edge? Straight, straight, not so straight. That would be the group failure. But then instead of failing like this, it's possible that an individual column could fail. Or it could fail into the page. Okay? So the reason that when we check the individual failure, we always assume k is equal to 1. And for the group failure, we don't. We assume we try to calculate. We use the alignment chart to find what the k is. But when checking failure of a sway frame, let's see. The reason we use a k equal to 1 for the individual failure instead of some k less than 1, because, for example, this column could also fail as a k equal to 1. You'd say, but hey, there's more stiffness up there. That's a moment resisting connection up there. Those beams would want to help it, right? The answer is yes, they would want to help it. But we're assuming that all of that stiffness is already given to resist the sway capacity, to resist the group capacity, the group failure. So when we go and check the columns as individuals, we always use a k equal to 1. The reason why we do this is because we will likely need the stiffness of the beam to help resist the group failure. So a simplified version of the structure above, we would take all the load and put it on, we would think of this like summation of P load on top of this member. We would work it as an equivalent rotational spring up here with all the load that's on top of it. And this spring accounts for all the beam stiffness. We're donating all beam stiffness. This is the sway. This is the sway failure or the group failure. This is this failure. Okay? And then we'll be checking the no sway failure, and that could be in the plane or out of the plane, and that's the same thing as that failure. Yeah? Huh. Why do we assume this is a pin at the top? Because we've given all of this stiffness from the individual failure and given it to the group failure. Okay, so let's look at some other notes that I handed out earlier today, and we'll come back to that and talk about it, and we'll hopefully it'll all make sense. So I'm going to give some examples. And sometimes when I teach this lecture, I have these as blanks, but I didn't do that today. Okay, they're already filled in, but let's be active. Let's hopefully understand what's going on, and you know, don't just sit back and go to sleep. So we have a frame, and I'm only drawing a single frame. Okay, and we have a column 3, column 1, and column 2. 1, 2, and 3. And I'm going to tell you the sway capacity are these values, and the minimum pin capacity, that's with the K equal to 1, are these values. Okay, so how did I get these values? Well, I use the alignment chart. What does the alignment chart give us? What do we get out of the alignment chart? K. The alignment chart gives us K. And from that K, with KL over R, and be careful, we have to make sure we use the right R. Sometimes we have to make sure we use the right L, too. We can calculate a capacity. So I used the alignment chart, and I found all of these capacities. Yeah? Yeah? And then I used a K equal to 1. No alignment charts needed. Assuming a K equal to 1. And I found all these values. Why did I do it that way? Because this is like the individual failure. This is assuming it fails as an individual. Okay? This is assuming that all stiffness are given to the sway capacity or the group capacity. This is assuming if every single one of these is a pin column. And you're going to say to yourself, but it's not. And you're right. It's not. But we're assuming this is the worst case scenario so we can give all of the sway capacity, all of the stiffness for sway capacity. Does that make sense? Okay. So if we do that, we're gonna take, let's say I take 200 kips and I put it on top of column 1. 200 kips. So then I have to ask, what's going to happen? Well, 200 kips. If I put 200 kips on column number 1, 200 kips is greater than the sway capacity, right? Right? So what's going to happen? Is he going to fail? No. Why not?
Its pin capacity wasn't reached. And
pin capacity wasn't reached, that's right.
The system takes the sway.
That's right. Column 1 wants to fail. Column 1 is unhappy. It wants to fail. Okay? It wants to fail. But column 3 and column 2 say, you're not going anywhere, brother. Because if you go down, we all go down. And that ain't happening on my watch. Right? So what we compare is we look at the capacity, the sway capacity. 300 plus 200 plus 100 is 600 kips. And this is what we say is the summation of P capacity. And what you're going to compare every time is the summation of P load, the sum of all the loads on top of the columns, to the summation of P capacity. And if the load is higher than the group capacity, then it'll fail. And if the load is lower, it will be safe. And if the load is higher in any of the individual capacities, what's going to happen? It'll individually fail as a pin column. So let's go through these examples here. And this is how real things perform. Real things act. So I say column 1 is overloaded and it wants to fail, but it's braced by columns 2 and 3 are helped. Okay. So now let's say I increase this load to 305 kips. What's going to happen? Well, it fails. Why does it fail? Because 305, well, 305 is less than 600, isn't it? So it doesn't fail as a group, but it's greater than the individual capacity. Think back to structural resiliency. If the individual is overloaded, you'll have failure. Or if everything in the group is at its limit, you'll have failure. The individual is overloaded. So column 1 fails as an individual column, as if it is a pin-pin column with a k equal to 1. And there'll be people somewhere and you say, but it's not really equal to 1. The k isn't really equal to 1. Right? It's got more stiffness there, but we're assuming we're giving that stiffness to the group failure. Okay? Now, what's going to happen in real life? You guys are in the graduate class. You guys are in the highest steel class we teach right now. What's going to happen in real life? That stiffness is going to go where it's needed. Therefore, if we might have said, and we will still continue to work problems like this in this class, okay? But if these columns are not highly loaded, then the beams won't help them. The beams instead will jump in, lower the K of this column as much as they can to try to make it safe. Does that make sense? But how are we going to work the problems? We're going to assume a K equal to 1. Why? Because it's a pain in the butt to... This doesn't happen very often. This almost never happens. In a real structure, what happens is everything's pretty uniformly loaded, or pretty somewhat evenly loaded, depending on its tributary area. And what usually happens is things don't usually fail as a pin-pin column. What usually rules the day, especially if you have frames with lots and lots of pins at the top. And one moment connection. Yeah? This is much more common in current construction techniques today. Much more common. So you're going to check each one of these as a k equals to 1, because that's what they are. And then you're going to look at this ability for group capacity, right? For sway capacity. And loads placed on any set of columns contributes to this sway capacity. I'm sorry, this summation to P. You have to have enough capacity, sway capacity, to resist these other ones. That'll make more sense coming up. Great. So let's say I add 301 over here, 100, 200. We add these up. What do we get? 601. 600 is the capacity. What's going to happen? It's going to fail as a group, right? It's going to all lean over, and they're going to fail as a group, and it's going to look like that. Column 1, 2, and 3 are at the sway capacity, therefore not able to brace each other. Group failure. Okay? So now let's say I just put 500 kips over here. Well, this is column 2. Pin capacity for column 2 is 600. 500 is less than 600. We're good. Summation of P capacity is greater than the summation of P load, no failure. If say it changes up to 601, I say it fails. How's it going to fail? That's right. It could go either way. Well, that's a good question. When we say probably would. Probably would. It's going to be whichever one has more imperfections is going to happen first. Okay? And I'm going to guess that it probably fails as an individual. But if you have a building and the individual column fails, that's pretty bad. Right? We would definitely call that failure of the system. Right? No one would like their building to lose a column. So we need to have an engineering, amusement park so you can see what this stuff would be like, right? I just want to build an amusement park. So let's say I take 500 kips, though. Instead of putting it over here, I put it over here. And I say, hey, there's no failure. Because the summation of P, the load on it, is less than the summation of P capacity. So I'm good. Okay, so now let's do this one. I put 700. I say it's going to fail as a group because 700 is greater than 600. And I draw the deflected shape. And now I put 200, 200, and 201. Well, again, I'm comparing summation of P of my load to summation of P of my capacity. And if it's greater, it'll fail as a group. Now, we're going to change things a little bit, and we're going to add a new flavor. We're going to put a pin. If we have a column that has pins at the top and pins at the bottom, it's still going to have a pin-pin capacity. But it's not going to be able to contribute to the group. Can't help you. If this column wants to fail, and it asks for help from this beam cannot be restrained by this column. Cannot ask this column for more help. And that's why we call these columns these pin-pin columns, a pin at the top and a pin at the bottom in a sway frame. That's why we call them leaner columns or wiener columns. For people that are not understand what I'm saying here, wieners do not have a lot of capacity, right? People that are wieners, you wiener, you can't do much, right? So a leaner column is one that doesn't contribute. It doesn't contribute to the sway capacity. Does that make sense? Okay, so that just means we have 300 plus 200. 500 is now our sway capacity. And we still have our individual pin-pin capacities. So let's say I take 200 kips and I put it on the top, the column in the center. Now, just because the 200 kips is on the column in the center, and just because this one has no sway capacity, doesn't mean it's going to fail. Because it wants to fail. It wants to lean over and fail. But it's restrained. It's held up by these other two columns. It's held up by these other two columns. This thing wants to fall over really bad. But it's being propped up by the other ones. So, again, we just compare summation of P capacity, which is 500, to the summation of P load, and there's no failure. Let's say we take it to 301. Now column 1 is going to fail as an individual. Right? Pin-pin capacity is 300. I take it to 301. It's going to fail as an individual. It's going to fail as a pin-pin column. Now let's say I put 300 and 201 out there. It's going to fail as a group. The capacity is less than summation of P. 300 and 150. Now it's okay. Summation of P capacity is greater than summation of P. So that's what you're going to do every time. When you see one of these frames, you're going to find the sway capacity, and then you're going to find the individual capacity. And then you're going to look at all of the load that's on top of the structure. And you're going to compare all of the load to the summation of the sway capacity, and you're going to compare the loads on the individual columns versus their individual K equal to 1 pin-pin capacity. And again, I know there's parts of you that will scream inside of you, not on this project, but not on this problem, because this is truly a pin-pin capacity. This is truly a K equal to 1. But I know there's parts inside of you that when you look at a problem like this should say, that's not exactly right. And you're right. It's not exactly right. But it's the assumption that we typically make when we're solving problems like this, so we don't have to work the problem exactly right. Okay? Okay. So I got a couple more examples in here. Let's see. Change things again where I have 2 leaners now. That's not that interesting. And this is actually possible in sway frames too. In non-sway frames. If I have something like a moment connection, I'm not sure why you would ever do this in real life. You would make everything get pins everywhere. But if you're analyzing a structure where this is the case, okay, it's possible to look at these as individual pin-pin capacities, and then it's possible to have a group capacity as well. Okay? That's possible to do. So, in summary, in a frame, the following requirements must be satisfied. Each column must support the load as a pin-pin, aka K equal to 1. And you're going to check this, and this is important. You're going to check this in both failure in the x and y axis. You're going to check failure of this column in the plane and out of the plane, into the page. You're checking both. Because as a pin-pin column, it doesn't matter. It could fail in either direction. Now, when we check things as a group, we typically check them in a plane. We would say this whole plane has a certain sway capacity, a group capacity. Is there any questions before we head on? No. Okay, so let's go back to our other handout. Now, I'm going to work I guess I started working this problem out here. I said, is the following frame sufficient? I showed 200 kips on each one. I gave you beams, I gave you columns, I've shown you in 3 dimensions how the beams are oriented and how the columns are oriented. This is what we would be calling in plane, this is what we would be calling out of plane, and we'll talk about what you can do with multiple bays in the future, okay? First we're just going to stick with one, all right? Oh, that's the future. So, now, we only have a single bay. We've got some information about how the columns are oriented. I believe, let's make sure we get that right. They're oriented like this, and like this. Our beams are oriented like this. That will become more important coming up. And we said we're going to use a certain technique to solve these problems. Now, I typically solve for the pin-pin capacity of each column, and then I solve for the contribution to the sway capacity of the column. This is a very simplified system where the pin-pin capacity is the same for all of the columns. So what do you mean they're the same? They're oriented different directions. So how can the pin-pin capacity be the same? I'm going to turn the question on you. How come? That's right. And it could fail into the page or out of the page, right? Right? It could fail like this, or it could fail into the page, or it deflects purely into the page. Yeah? So now we'd have to check, is it buckling about the x-axis or the y-axis? Well, since all of the L's are the same, and the RX's and RY's are the same, there's nothing bracing or stopping it mid-height. And so if we're assuming the K's are all the same, then it's going to always buckle about the weak axis. It's going to always buckle about the weak axis in this one. Now when I go and work this next problem, where I put a cross brace in it, that's not going to be the case anymore. Okay? Things are going to get a little bit different in this one. But not so much for this problem. So I know it's going to always buckle about the weak axis. And I know that my K for my pin-pin, my no sway failure, my individual failure is going to always be 1. So I'm going to have my KL is going to be 40, and I can use table 4.1, my friend, and I'm going to find my VPN is 232 kips, which is greater than 200 kips. Therefore, we're okay, right? It's not going to fail as an individual. Yeah? So what's next? Sway capacity, the group failure. Now, I start to look at each one of these columns. And now, it highly matters how these columns are oriented. And we think about them just failing in the plane. And actually, we should probably try to draw a deflected shape. So forgive me for this already being here. And I'm going to draw a deflected shape that looks something like that. This one's going to go over equal amount. This one's going to go over equal amount. Now we know this column has a pin at the top and a pin at the bottom. So for sway, what's the K? Infinity. The K is infinity. What does that mean the capacity is?
0.
0. For sway, the capacity is 0. Sway. Contribution to group failure. Why? What kind of column is it? It's a leaner column. Wiener column. So they're straight. Those columns go over and they're straight, and you will have to draw the deflected shapes you should draw it on your homeworks. You're going to have to draw it on the exam. Looks something like that. Great. So now I go into my alignment chart corrections, and I'm going to start to use, I know my K for this, I know my K for this, I don't know what the K here is. So I'm going to use P over A. I'm going to find out what the stress is. My tau comes out to be 1. My G bottom is infinity. My G top. Now, my tau is 1. I have an I over L. Which I am I going to use? IX or IY? This is real important. If you don't understand, you're going to miss every problem.
IY.
IY. How did you know?
In that way.
Because when it buckles, for it to buckle, it's going to have to move over here, right? It's going to have to bend. If you can think of the bending occurring, this bending in this member, it's going to have to bend about the YY axis. So we know this is IY. This is IY. This is L, which is 40 feet. Okay, so now I have a beam. How many beams do I have? 2 beams. Here and here, right? Okay, so the beams, what are they going to bend about?
X.
X. They're going to have to bend about their x-axis, strong axis. So I know this has to be IX. This has to be IX for my beam. Okay, so now I have an M factor. My denominator is 6 because it's a sway frame. My numerator is 3 because of the deflected shape. 3 over 6, IX over L, and I have 2 here because I have 2 beams. My G bottom is infinity. G top is 0.81. So I use the alignment chart, and I get a K of 2.3. Now, I'm going to go ahead and calculate. This is a KL over R calculation. KL over R. And which R am I going to use? RX or RY?
Y.
RY. How did you know? Because that's the axis it bends about. So that's KL over RY. Calculate my F Euler, which is 1.7 KSI, which is less than 0.44 FY, which means I'm going to use this equation and I get 44 kips. So my summation of P was 200 times 3, which is 600 kips. My summation of P capacity is 44 kips. 600 kips is greater than 44 kips. Fails. Make sense? Awesome. Let's do another one. I think I have 2 more examples that I'll blow through fairly quick. This is what I would say is a more conventional problem, because it's a true frame. Now, when we go and work frames and frame problems in real life, the first question we have to ask ourselves is, what kind of diaphragm do we have? What's that diaphragm made up of? The reason why is because if this material is extremely flexible, air, for example, then if this frame wants to fail in this direction, then the back frame doesn't help it. Let's say we have something very stiff in there, like concrete. It's a common diaphragm, right? Common flooring system. So if we have a concrete flooring system in there, and we overload this front frame, and the front frame wants to fail, for it to lean over, it won't be able to, unless the back frame leans over as well. Does that make sense? So if we have something like a rigid diaphragm, then individual frames, when you look at failure, you have to look at the contribution from the front frame and the back frame in a certain direction. Let's say I have a flexible diaphragm. What are some examples of flexible diaphragms? Wood. How about really thin sheet metal? When's that used? On a lot of roofs. Oftentimes you don't rely on sheet metal roofs as being rigid diaphragms because they're like, paper thin. And they're supposed to be attached everywhere, but they're often not attached as often as they're supposed to. So if you have a thin roof deck, and you want to make it a rigid diaphragm, how can you do that? Cross bracing in the roof. You ever seen that before in industrial buildings? Go up and you look. Talk about something that doesn't cost very much. We run these really thin wires in between. And that's enough to consider a rigid diaphragm. That's enough to consider it. I mean, you get a lot more capacity out of that. Okay, a whole lot more capacity. Now let's say something horrible happens and a debris falls through and cuts the cables. You're in trouble now. But in a lot of metal buildings, they're not necessarily designed for extreme events, right?
Are most of those designed, like, say in that picture how there's two bays, a lot of times will they only put one cross brace in one of the bays and not both bays?
Yeah, you don't need them in both.
You don't. Well, I know you don't need them both, but like, do they usually say distribute it to put like something like instead of a heavier brace, like a thicker wire? I guess would they do like two smaller ones for safety precaution?
So first you're going to learn how to design bracing on Friday. Okay? Mm-hmm. So you're going to learn how to design these members on Friday. Mm-hmm. Okay. And what you're going to find is that you don't need much. Even for heavy loads, you don't need very much. Mm-hmm. So the only reason why they'd ever put in two was if they were concerned that something might happen to one of them. The other thing I've seen that's really unfortunate is that's a great idea to do that, and then they'll run a single cable from here to here, and they'll run another single cable from here to here, and say, oh, that's a good thing. Well, if something happens that causes both cables to break in this bay, there's going to be nothing that holds them in these bays because they're single cables. They're not different connections. They'll run a single cable through. That's a very common detail. It's a very poor detail. Well, it's a very poor detail if the goal is to provide a number of different cross braces. If sometimes what they'll want to do is they'll want to minimize racking. Okay, they'll want to just stiffen the entire structure up. It's more for drift limits. Then that's a fine detail to use for drift limits. But I've seen it used before for cross brace, not for drift limits, and they didn't quite understand what they were doing.
Mm-hmm.
Does that make sense?
Yep.
Okay, so in every one of these problems, I should tell you if it's a rigid diaphragm or a flexible diaphragm. And if I say flexible diaphragm, what's that mean? That means the front frame handles itself, the back frame handles itself. Yeah? And if I say rigid diaphragm, that means the front and back frame work together. Now, in this class, we will often, typically, only check things either in the plane or out of the plane. In real life, you'll check both. You'll do one set of calculations for in the plane, then you'll just do another set of calculations for it out of the plane. Okay? Okay, so this is a more traditional approach to the problem, and we're going to talk our way through it, and we'll get out of here. So we're going to start with column number 1, and we're going to find the no sway, or you could think of it as the pin capacity. And we're going to look at it in plane and out of plane. Okay, so if we look at it in plane, that means it's failing about which axis? What axis is that? XX axis. Okay, so if I'm going to use table 4.1, which is I like to do, I'm going to need to divide by Rx over Ry. Why? Because table 4.1 is derived with respect to failure of the weak axis, not the strong axis. So I use K equal to 1. Remember, that's the conservative number. L is 20. My Rx over Ry, I get 9.47. My phi PN is 600 kips. Now I look at it out of the plane. Now, I'm going to take the conservative route that we talked about. I'm not going to use the alignment chart because, remember, I might need that stiffness for something else. So I'm going to imagine that this is just a pin column at the top up here with a K equal to 1, an L of 10. So out of plane, I'm going to say K is 1, L is 10. My KL is 10 feet. I can look it up in the table 4.1, and I get a capacity of 590 kips. That's going to control for the K equal to 1, for the non-sway, for the individual failure. And now let's look at the sway capacity. So this is the sway capacity, and we're going to say this has a flexible diaphragm. At least that's the way the problem has been worked. So you can imagine that there are no cross braces. They're gone. Nothing there. Air. Got nothing but air. For this problem, we only have to check in plane. In real life, we would rework the problem looking at each frame in the out-of-plane direction as well. So you have something that looks like this. And also, I just want to say that you would never, ever build a modern structure. Why can't I see anything here? Oh, no, I can't. You would never build a modern structure with MoMA connections everywhere. Ever, 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 ever. Unless you want to get killed. Okay? You would put pins every place you possibly could except for one. Okay? And we're going to do that coming up. We're going to do that, I think, in the next problem. I do that right here.
What do you mean by you'll get killed?
People will be very upset with you because the cost of your structure will be very expensive. Because every MoMA connection is about 10 times the cost of a pin connection. So the cost of your structure has just gone up by 1, 2, 3. It's 4 compared to 1. It's 4 times higher than it needs to be. So people will be very upset with you. Your owner will be extremely upset with you. Your client will be extremely upset with you. Yeah, well, the cost will come in. Well, they don't care. They'll do whatever you pay them to do, but they won't like it. They'll say you don't know what you're doing. But the cost will come in at a lot higher per square footage, maybe twice, 2 to 3 times the dollars per square footage, and the owners will be like, "Whoa, I'm building the same area, and all these buildings cost about $120 a square foot. Why is yours $240 a square foot?" It's like, oh, I put MoMA connections in all the frames, and they'd be like, "Don't do that. I'm never going to hire you again. You're fired." Okay? Okay. So, for this problem, we only have to check in plane. In real life, we would rework the problem looking at each frame in and out of plane direction. G bottom, so I redrew my little column. I'm looking at this. The strong axis is oriented like this. G bottom is infinity. Tau is equal to 6.41. I'm sorry, my P over A is 6.41. Tau is 1. I plug into this equation. I didn't draw my deflected shape. I need to draw my deflected shape. So if that member comes over and looks like that, that member comes over and looks like that, that member comes over and looks like that, this will go down, up, down, up, down, up, down. Think of this having to be 90 degrees, this having to be 90 degrees, this having to be 90 degrees. The only way to hook them together is to go up and down. The only way to hook these together is to go up and down. Okay, so for that reason, my M is 1. Meets the assumptions of the alignment chart. So when I go and use this should be the I of my column. Which I should I use? IX. Good answer, class. When I use I of my beam, what should I use?
IY.
Yes. Should be IX, shouldn't it?
Yep.
The beam is going to be bending about its x-x axis. IX. Now I'm going to use an L of 20 feet, the entire L. 30 feet for my beam. My G top is 3.72. My G bottom is infinity. My K is 3.1. Now that I have my K, I can calculate my KL over R. I'm going to use my RX over RY. How come? Buckle out at strong axis, and I want to use table 4.1. You don't have to if you don't want to. There's the K, there's the L, there's my RX over RY. I get 29.4. For my table, I get 184.5. I'm just showing my interpolation down there. Okay. Keep going. Column 2. Said my in-plane failure is going to controls by inspection because L in-plane is equal to L out-of-plane. I don't have that silly brace in the way. So I know my minimum is going to control. It's going to buckle about the weak axis. So I can just look up the KL, and it's 353 kips. You okay with what I just said? Okay. So in my sway capacity, my group capacity, this is what my structure is going to look like. And it's buckling about the, let's see, it looks like that. And then these are all about their strong axis. So these are going to be IXs. IX. What's this going to be?
IY.
L is 20, 30, 30. M is 1 on all these. I get a G top of 0.42. K at 2.2. Since it's buckling about the IY, I can just use K times L. I get 44 feet. Not in table 4.1. What do? Use the equation. So So I use pi squared equals K over R squared, blah, blah, blah. Get my capacity, 78.8 kips. Now, at this point, I know that my load is going to be what? 300, right? 300 kips, 100 plus 100 plus 100. And I know that my sway capacity from column 1 was 184. And my sway capacity from here, I'm not there yet, am I? I need to keep going. Okay, so my no sway capacity is going to be the same as column 2, 353. So let's keep going. I redrew my little column here. I know this is going to look like this, and I believe this is going to look like that, right? That's how it's oriented. How did I get that? It's given, right? Oh, I drew it wrong. Good thing I checked. That's wrong. Looks like that. Always good to check. Okay, so now I have tau is 1, m is 1. I've got my g top, and this is I of what? It's I of the column.
Y.
IY. And this I is going to be of what? The beam? It's going to be IX. I get 0.84, I get a K at 2.35. Be very careful to make sure you do not use the wrong alignment chart on the exam. There's an alignment chart for sway and there's an alignment chart for no sway. When you're checking the group capacity, in this case, you're checking the sway capacity, right? So you need to use the sway alignment chart. K is 2.35. Again, this one's not in the table. I'm going to use my equation, and I get 69 kips. Now, I highly, highly recommend making a table. Highly recommend not only for your organization, but for your grade, to make a table where you have your non-sway capacity, you have your sway capacity, and look, when you total it up, we get 332.3 kips, which is just greater than 300. Frame is okay. Does that make sense? Okay, so let's work the same problem, only I'm just going to add some pins in. I'm going to take some loads off. Columns, beams, FY50 KSI. It's the same problem as before, only pins were added at columns 2 and 3. We can therefore use a lot of what we already know. First of all, doing any of this, does any of this change the pin capacity? Not at all. So we can reuse all of that. And they were good before, and the loads got lower, they're going to be good again. Let's talk about sway capacity. Now, let's see here. I say my non-sway capacity is still this, but now my sway capacity of column 2 and 3 becomes 0. Why?
Wiener columns.
Leaner wieners, right? Okay, but now column 1 still gives me something. Got this non-sway capacity, it didn't change. Now I got to find the sway capacity. So let's draw the deflected shape. So if this moves over, this moves over, this moves over, this has to be straight, this has to be straight. So that means the beam's going to be what? Straight as an arrow. Okay. Now let's do this one. This one's going to be whatever it wants to be. This has to be 90 degrees. This is going to deflect out and then back in. That's a deflected shape. You're going to be required to draw that on the final. So my tau is 1, my M 3/6. Remember the 6 because it's a sway, and the 3 because that's the deflected shape. Got to get good at picking out the M off your deflected shape. That goes here. Which I do I use for my column? IX. Which I do I use for my beam? IX. 7.45. G bottom's infinity. K is 4. Okay. Now after I have my K, I have to find my KL over R. I'm dividing by RX over RY. How come? Spinning about the strong axis. Okay. So I get 37.9, which is about 38. Phi PN is 104 kips. So for the columns, sway capacities are still okay. I'm sorry, the non-sway capacities, the individual failures are still okay. Sway capacity is 104, 0, and 0, but then I compare 104 to 105. The frame's going to fail in sway. It's going to fail as a group.